Yeah, so this work, as I say, is a part of I didn't think it's a part of my PhD, and I don't have results from the model yet. So what I present is like an ongoing work towards validation of the model. And I want to start first by a little bit of context. So I'm working on this area, Southeast Asia, and I want to. So this is a domain I work on, and this is also I go to Vietnam regularly to work with a scientific team there. So just some things about the area. So in terms of from the atmosphere point of view, the topography is quite complex, and you have some phenomena that makes the region quite complicated to study, especially for the computing resources they have there and that they use there. You have the summer monsoon with a north easterly wind that brings precipitation in the yellow area. You have a winter monsoon as well with almost opposite wind patterns, like southwesterly winds that bring precipitation in these yellow areas. In addition to that, you often have typhoon tracks that you have more or less following these arrows regularly. In every year you have typhoon tracks this way. And from the ocean side, the bathymetry is also complex. Besides, you have the global thermohaline circulation that cross the area. So it's like you have numerous straits with more or less depth and that are more or less narrow. And so the South China Sea, there is a lot of surface interaction in the South China Sea, like that plays a role in the modification of the water that go through via the thermohaline circulation. And you also have different upwelling phenomena that add to the complexity of the system. Besides, this is regions which is directly influenced by the ENSO in the Pacific, the IPO or other wider scale oscillation. And all of this is about a region which is quite new economically, and this also means that the science community there is quite recent. And in particular, when you look at computing resources, so for example, there is not a lot of oceanographer that works, local oceanographers. They mostly work on the atmosphere, and when they address the topic of this full region, like all this region regionally, the resolutions they work with is about 20-25 kilometers. So it's much more modest than what we can work on in Europe. And I am actually working with one of the scientists there, which is a climate modeler. It's Thanh Ngo, who works in USTH in Vietnam. And my work is the result of a collaboration between Thanh Ngo, who works in climate modeling, and Marie Nerman in Toulouse, who is an oceanographer. So these two researchers, they do a lot of partnership to try to use the resource we have here in Toulouse, especially for working in the ocean. And there's a lot of works happening between them. National laboratories as well, which is called the Lotus. And although they have not worked with the coupled modeling approach yet, only either on the ocean uncoupled configuration or atmosphere uncoupled configuration. And so my PhD is trying to make the links between the two worlds with trying to bring a regional coupled approach, as coupling here, in the Southeast Asian climate. So the idea here is to on the mid-long term to provide a tool for the community that works on this area and with the local scientists there for working with RC coupling. And for my PhD more specifically, the idea is to try to characterize the contributions or RC interaction in the climate. So when we think of the RC of coupling, the models they use in the area, there are 3 steps that comes to us quite straightforward. The first step is the technical development. This is something that's done. So we use, the idea is to go as simple as possible with by using the models the community is already used to in this area. So in Southeast Asia, the climate modelers use RegCM, which is provided by the ICTP in Italy. In Lagos, we use Symphonie for studying the ocean. Symphonie is not distributed. It's a local model where the team is very little, so it's very convenient to work closely with the developers and so on. While for RegCM, it's a widely distributed model, and but I'm in contact with a lot of users, Southeast Asia, that use it. For the coupling, I use OASIS provided by Surfax, and it's we go as simple as possible. The surface currents are not implemented yet for the feedbacks of the ocean, because we use the bulk parameterization for the surface which is already implemented in RegCM, and so far this feature is not implemented yet. And so once the technical development is done, it comes to the parameterization and validation. This is what I will talk about today, so I come back to it in a minute. And the step 3 is, once we will have validated, is to characterize the added value of such a coupled model. This is not something I've done. However, I have planned the technical aspect, the technical protocol that we will follow, which something like that. The idea is to compare the coupled run to an uncoupled run, but to separate the added value of the high resolution surface temperature, to separate this added value from the added value of the coupling itself, the fact that we have the feedback from the atmosphere, from the ocean in the atmosphere. And so the idea is to have a common spin-up run coupled that will provide common restart files for first a coupled run. So basically just using all the setup that I've developed. Second, do an uncoupled run using the forcing at the interface that comes from the coupled run, that comes from the first one. So that between the 1 and the 2, the only thing that changes the fact it's coupled, but the signal has the same foundation in the same resolution. And the idea is that we could then lower the resolution of these outputs from the coupled run to have the number 3 here, which has the only difference is that the forcing between the 3 and the 2 are in different resolution. And we would compare this to the reference run ultimately, which use the usual forcings that were used so far. And so the idea is that there is one type of change between all of this simulation. From the 4th to the 3 is just the source of the forcing that change. From the 3rd to the 2, only the resolution change. And so we can really see the only impact of coupling when comparing the first run to the second. From a technical point of view, I use a feature in OASIS that is initially designed for debugging, I guess, which is the XBout option when we couple the fields. And I've just done a modification in the OASIS code to make this. So basically, it means that the interface, the fields that I exchange are outputted at each coupling period. And if I don't do a modification, there is only one file per fields during all the simulation. And so it takes more and more time as the field goes up. So I do a modification to make like one day per field, so I can store these files and use them for the second run later. So this is done. It's just this is ready. It's just that I've done. I have not the validation yet. So here we are. I start with parameterization. So the idea, I say we want to make it as simple as possible at the beginning. So we have two configurations that are used and validated in the region, one in the atmosphere, one in the ocean. So this is the configuration they already use, so I don't change their resolutions, or I trust the communities of both sides regarding the schemes they use and so on. So here I've put the details. For the ocean side, it's a bit more messy to find the reference of each schemes, but Marcel has done a lot of publication on his model, so if you're interested, you can look at it. And the idea is that, yeah, basically I put the coupler in between. I use bilinear interpolation, 1 hour coupling period, and I transfer averaged field over on the hour, not instantaneous, to keep for conservation. And I'm thinking, okay, it will be all right. And the thing is that the first result we have is the result on the left is SST average over on summer after 1.5 years of simulation, and on the right it's a comparison. It's Copernicus from Mercator, and so we can observe like a 4-degree bias in the middle of the so this is a bit disappointing for me, who developed everything. But the good news is that actually I thought it was not a detail, but I changed the version of the atmospheric model, thinking that I want the development I did in the model to be maintained as much as possible. So I wanted to take the most up-to-date version of the model, and actually it introduced differences, and it was not the version that was validated. So when I come back to the older version of the model, it's better, but it's still not here. I have like 0.7 degree average over the year. And locally, it can reach more by. So globally, so it's better if I keep looking at just the summer. But what strikes me is a bit later in the year, when I look at December and I do the bias with Copernicus on the left, it reaches at actually 3 degrees in the south, and I directly link that to the bias in surface solar radiation, comparing to the reanalysis from ECMWF, where I see that there is this kind of patterns that seems to be directly linked to the bias in SST. Actually, when I look backwards in the years, this patterns in the radiation, surface radiation, comes from September. Here's September, and it's developing of the month, November, and here again December. So I'm trying to look more in detail. When I try to sum up all the things that go wrong, there is a big list, like there's a lot of things to work on. I don't think I go into detail. The biggest problem are the surface latent heat and the surface shortwave that are quite significant. Latent heat, we have a direct consequence is that in the surface salinity, we have much more salinity at some point because evaporation is too high. Probably also linked to the bias in the wind speed that we have in the atmosphere. So here I'm starting to realize that the configuration that I was starting with in the atmosphere is not reliable at all, and I've been advised to use it and so on, but I'm trying to understand what happens, and actually it's just that the validation criterion was not interesting for me, that was doing a couple model, because we validate in the model temperature, precipitation, and 850 hectopascal wind. So there is nothing regarding surface fluxes or radiation or clouds or stuff like that. And so I really like started to realize that, and so the idea from here is to go back in uncoupled uncoupled runs to try to validate the uncoupled configuration of the atmosphere. And so this is and I'm firstly being advised that maybe like a big uncertainty in this kind of model where convection is unresolved and parameterized is the convection cumulus scheme. So I start to do sensitivity with cumulus convection schemes. So this is what I do from here. I'm testing 3 different schemes, and I look at many variables, but here I printed shortwave patterns. These are the same as on the right here, except it's actual patterns, not the bias. And the ECMWF reference is on the down on the lower plot. So you have 3 different cumulus schemes with the December average of the radiation, and I see that the problems. The patterns that is a problem for me that would have a direct influence on SST when I couple is still here. It's a bit lessened on the Emmanuel scheme. But the thing is that Emmanuel scheme introduces other problems. Like it's also the run that gives me the worst precipitation and the worst near surface temperature. So I'm not happy with that, and I'm understanding that the problem is not only will probably not be solved with cumulus convection scheme sensitivity test. And so I'm thinking that basically I don't have unlimited resources, so I must make choices when I choose to do sensitivity test, especially as I'm doing a test with uncoupled configurations. Then I will have to do test with the coupled configuration, so it will take a lot of resource. So I need to think a bit better to take decisions. And so I try to link this to look closer at other variables. I look at the cloud fraction, and I try to understand where it comes from, because we can see the boundary effects on the center and right plots are here, which implies the fact that basically the humidity provided by the boundary condition doesn't match what's happening in the middle of the model. And basically, when I look at clouds, I see that clouds get stuck near the boundary. So there's a problem with what happens with moisture in clouds. So I try to understand where the cloud fraction comes from. And the 2D cloud fraction I see, basically, it comes from a 3D cloud fraction, which is we do the product of clear sky fractions along all the columns to get this. To get that, and this 3D cloud fraction is actually the maximum between different sources of cloud fraction in the model. I don't know if it's the same everywhere, but and basically there is a resolved scale cloud that give a cloud fraction, the subgrid scale clouds that give another cloud fraction. We take the maximum, and this is how the model have a cloud fraction to give to the radiation scheme to calculate what's interested for me afterwards. And the thing is that when I look at the cumulus convection scheme inside the code, because I couldn't find that in the documentation, I had to look inside. The problem is, what I noticed is that there is a maximum cloud fraction that the cumulus convection scheme can bring, which is 60%, and that the cloud fraction I was noticing in the model was clearly above. So here I understand that actually cumulus convection scheme will not solve my problem, because the high cloud fractions I see are necessarily from the other side, which is the moisture scheme. So if I want to solve my problem, I need to focus on sensitivity with moisture scheme, and maybe also on the cloud fraction algorithm. And so basically this is where I'm currently at. I cannot do a more up-to-date presentation of what I'm doing. Actually, currently some things are running regarding sensitivity tests on these 2 aspects, and it's quite encouraging. I have found a moisture scheme which is better for my work, and but globally this is the idea. I couldn't make a scientific presentation because I didn't have scientific results, but I found that interesting that there was a presentation this morning that shows showed errors in lesson that they learned from their parameterization. I think it's a good thing to see that yeah, everything is not perfect at the first place. So I'm as a conclusion, I don't have a lot of things to say. I just hope that I can have this regional couple model validated soon, and that I can do something at the end of the PhD. Anyway, at the point we have to put a stop and take a decision, because we can not do sensitivity unlimitedly. And so I'm just, I thank you for your attention. I think if you have questions, I can answer them. And if you have remarks or advices, I'll be very happy to hear them as well.
Thank you for allowing me to speak here in this community. This is, I think, my 4th or 5th time in this series of workshops, and I've been enjoying it very much and learning a lot from all of you, because I see myself somewhat a hybrid between a user and a developer of coupled systems. And I am here today also on behalf of a large team at Virginia Institute of Marine Science and NOAA's National Ocean Service. Can I skip ahead? No? How does this work? Okay, let me just talk a little bit about modularity. So when I think about this coupled system, I am arguing for granularity of modular coupling at different levels. And there are basically 5 levels. So if we go from the left, we have lots of biological models, for example, for our ocean. I mean, that could extend to the land as well, but I'm a marine modeler, so I look primarily at the ocean. Lots of models that we have available as process descriptions. Then I will be talking about an interface, a generic interface for these biological components or ecological components in an ocean modeling system. And this ocean modeling system itself can be embedded via some sort of Earth system modeler coupler. It can be Earth system modeling framework, could be something else, in a system where also atmosphere, waves, runoffs, whatever, cryosphere are represented. So we have basically 5 layers. 2 of them are the coupling layers, those between the fine processes and the domain model, and those between the Earth system components and our ocean domain model. The case that I'm presenting is here just a specific implementation of an Earth system modeling system, and we've already seen in other talks that ESMF is just a tool that people have to work with and convert into a driver and realization of really an Earth system coupler. And this one is CoastalApp here. The ocean modeling system I'm talking about is the SCHISM, and the biogeochemical framework is the FABM. And this morning, I think it was Juan who already said that he coupled the ERSIM biogeochemical model into NEMO with this FABM coupler. Now, why do we worry at all? This is work we did in the past in our group, because at the coast, I think we have a strong interaction between the very fine processes of biology and the large-scale ecosystem processes. We've seen a significant effect of climate heating on the primary productivity of our regional seas. We have fine-scale effects of biology on the seafloor, on how much sediment is taken up by the ocean through resuspension, and then how much light penetrates the ocean, and that again has an effect on net primary productivity. Or we have these wind parks built here in the North Sea that change the current, change the turbidity of the ocean, change the productivity. And we want to know that for the future and be able to predict that, because we will be using politically our coastal regions as storage areas for carbon by regrowing seagrass, for example, or re-establishing the seafloor. which is heavily perturbed, at least in our North Sea. 2013, that was 9 years back, we, as biological, ecological modelers, didn't find our place in the Earth system community that we thought we did. So we came up with a new system. It's called Moscow. You've seen it before on one of the presentations, I think, by Dan, of ESMF couplers. It is yet another ESMF usability layer, and that made me think, well, maybe ESMF isn't so usable because we all write these new usability layers. But really, no, that's not what I want to suggest. It's more that it's extremely powerful as a common ground for many people to work on using the same technology, but then adapting it to their own needs. And we did that because we have lots of process uncertainties, huge parameter spaces, and we really want to have modeling systems that go from 0D. So making a simulation in a water bottle, which is typically what lab people do, to the global ocean, using the same modeling system. And I'll skip over that. There are lots of these modeling systems. The one on the left is the one that was used by our group for these North Sea processes. But we actually arrived at a stopgap where we thought, okay, the typical ocean models that we were using there are not sufficient. We needed to have unstructured models that really finally resolve the shape of the islands, the tidal channels between our barrier islands. And we completely changed our hydrodynamic system. Now, that shouldn't do anything, right? To a modularly coupled system, you just plug in another ocean model. Well, if that ocean model wasn't such a beast. And we switched over to a beast. And that is the SCHISM, semi-implicit cross-scale hydroscience integrated system. Why? Because it's cross-scale. It allows us to really do something at the 5-meter scale at the same time as doing something at the global scale in a unified model system, at least the ocean model system. And this is the beast. It's not only a hydrodynamic model. It has lots of components around it. It's a monolithic system. It's all coded in one Fortran. It's, okay, using Fortran modules, but that's not what I'm really talking about when I talk about modularity. Two things that were really disturbing to us is it had like 11 interfaces to biogeochemical models. It had only an incoming atmosphere. And of course, that is nothing that would make sense in an Earth system context. So the first thing we did is we used the FABM, which is we only have one interface now to the biology that could occur in the ocean. And FABM itself then reaches out to many existing, depending on, well, the version you use, 20 to 50 available ocean biogeochemistry models that you can actually just plug in and play. This is a non-exclusive list of what is possible, and you see RSEM somewhere. We don't see it.
Still on top.
Oh, it is there on top. Yeah, it's the standout model here. But there are many others. And, you know, they mix and match with many ocean model representations. Now, NEMO is one of them. ROMS is another one. MOM that you might be familiar with. Now, if you're a BGC modeler, yeah, you only have to maintain one code and it runs in many ocean models. If you're a hydrodynamic modeler, yeah, you only have to keep up with one interface to interact with all kinds of ocean biogeochemistry. That was very useful to us. And Zhengguan Wang at VIMS actually did a comparison of a hard coupling in the SCHISM modeling system with a modularly coupled approach using the same model. And yeah, we do have some drift here. You see the blue and green, they drift apart a little. Nothing to worry in the context of the data. Yeah, it's very uncertain in biogeochemistry still. So we're quite happy with taking the model apart, modularizing it, and saying it's valid. We apply that now, the system, also to our ALBA system at home. And here you see that we really resolve the individual parts of the port of Hamburg, for example. Hamburg is here. There's the River Elbe going into the North Sea, and then extending the simulation, seamless cross-scale to the regional ocean system. Now, on the other side, yeah, we had foremost the SCHISM only accepted input from the atmosphere, input from the waves. We now add an ESMF NUOPSI layer. We actually add both layers because we want the SCHISM to work in our old model system, Moscow, which is ESMF based, and in new NUOPSI systems that could be NOAA's CoastalApp, but it could be any of the other NUOPSI enabled systems like CESM, sorry, Mariana. Okay, any of those, of course. Right, well, some of these new applications, we just finished the interface, is we modularly did some data assimilation, taking advantage of mostly the fine time control that ESMF gives us in running multiple instances of the same model at the same time, generating, of course, ensemble averages, error estimates, and feeding it back through data assimilation comparison with data into another run. And this is a publication that's just out on one of the Copernicus journals, Geoscientic Model Development. Maybe you've seen it, Sophie. I hope that'll be published soon. We play around a lot with, very flexible I/O, something you'd probably do with XIOS or others. You have some input file and you do online calculation of the I/O, regridding. You get your temperature out in Kelvin usually, but you want it in degrees Celsius, but we really run out of space to store out the data. So we don't write it out in Kelvin, we just write it out in Celsius with online post-processing. All those things, comparison to station data, that is all now modularly done. This is a 10-component ESMF model that is just dealing with easily configurable. You've seen these configuration files from ESMF at runtime configurations. Now, this is another NUOPSI system now. It's CoastalApp developed at NOAA National Ocean Service. It's built or it's modeled on UFS as Ufuk presented yesterday. So the system should be in principle comparable. And this is a new system with several components working, and SCHISM you see here in development. Now what's basically new is before they did their simulations for inundation, coastal inundation, mostly compound flooding with 2D ocean models, which were working well. But now, of course, everyone wants to go 3D, so ATCIRC is replaced by SCHISM 3D. But there are other well-known models in the system, WaveWatch 3, you've heard about it a lot, that we are developing. And yeah, Hurricane Florence, that's kind of our standout test case. 2018 is in a very similar test system couple, and you've already seen these NUOPSI coupling lists, where basically you only give the processors your model runs on here on different partitions, and then you have these little arrows between the atmosphere and the ocean or whatever else you want to couple. Implicitly generate all the coupling, all the regridding without you as a developer having to worry about. Of course, highly simplified here. Now, does the video play? Not sure. No, I don't need to play it, so. Okay, basically, we now have the coupling to the NUOPSI-based CoastalApp. We have the coupling to the FABM-based biogeochemical model suite. We put it all together, replaced both the left side and the right side of the SCHISM modeling system. So we have a modeling system, FABM, for biogeochemistry, inside a ocean modeling system, SCHISM, inside a regional Earth system, modeling system, CoastalApp. So that gives us, and that was fresh off the press, that's the reason for version 1.2, because in 1.1 didn't have these results yet. They were produced yesterday morning. We actually have biogeochemistry, typical flagellate blooms in San Francisco Bay. This is what you see. You see how the system resolves many of the incoming rivers. This is just a test system, so in our productive system, we have much more of the incoming river system here represented. And in San Francisco Bay, we have the bloom here of flagellates, and you would see also that we have then the also measured oxygen minimum that is relevant for the area in the southern part of the bay. So that couple system is working. No?
No, yes, click yes.
Ah, that's fine.
Okay.
So what have I done? What have I shown? We are having these three aspects of modularity layers: a coupling system, a coupling system, a coupling system. We have different Earth system couplers here using the same biogeochemistry and hydrodynamics. One is NUOPSI based, one is ESMF based. And this is a new system, so it's in development. We are developing independently in all of these four boxes. All the developments are independent. Of course, we are testing the integration continuously. Now we have some biological work going on the left. In SCHISM, we are actively developing global mode. It's usually used for regional applications, but now we're going global. We're operationalizing it with the Taiwan Weather Institute and with NOAA. We are completing the interfaces. You can imagine if there are more components coming in, your data demands, export and import, might just increase. So that's just an incremental addition of interfaces, nothing critical. And we are also adding the basic model infrastructure into SCHISM. In CoastalApp, we are completing the interfaces. We're also operationalizing it with want to include CDEPs and switch over to CMAPS, the CESM system. And I hope Mariana can advise us on that. Working on generic I/O. And for my old baby, Moscow, which I started 9 years ago, actually I'm happy to make it obsolete. We don't need it anymore because much of that functionality that we were 8 years ago missing, we built in, has now been taken up. Well, not because we said we needed it, but their development was just more rigorous. In NUOPSI and ESMX, as Dan already said yesterday, all that is left for us to do is use this, take this coupled system, take out some of the components like generic I/O, which are still useful, and make them available to the Earth system modeling community. So we come up with an open, seamless, equitable, cross-scale Earth system model. If you have someone who would help us work on this, we are in need of a postdoc who is interested in doing that at VIMS, located in Virginia. As far as I've been following this, there have been constantly job openings, so send your students over there that you find suitable. How do I go back? That's all from my side. Thank you very much. Happy to take questions if there are any.
Introduction. I work at the Antarctic Research Centre in Wellington, New Zealand. We're a tiny modelling group of 7 people, 6 people actually, we lost one, trying to do everything from global climate modelling to ice sheet modelling, ocean modelling, atmospheric, biogeochemistry modelling, and sea ice modelling, and do this for the past, the present, and the future. And of course, by definition, that's impossible. So we rely heavily on groups or communities like this one to collaborate, or as I call it, steal, but really to use other people's development work. We are definitely at the end user end of everything that's been talked about today. And part of the reason why I'm here is to actually, figure out what my way forward is with this specific problem. So the project of coupling PISM to ROMS was part of a larger program by the New Zealand government, which was to assess the sea level rise damage or the sea level rise changes that are being expected for the next 100 to 300 years. This was to derive advice for local councils all over New Zealand, what they need to put into their long-term planning for roads, railways, beaches, access roads, and everything. It was a large program. Only a small portion of this program was actually put aside for science. And one of the goals in the science part was to improve sea level rise estimates for New Zealand. And the predecessor of that is, of course, to understand ice mass, Antarctic ice mass balance in the next 100 to 300 years. And my part was to couple an ocean model to an ice sheet model that we use to predict for the next 300 years. So it seemed to be a straightforward exercise. You need to take PISM, because we run it in the group, we understand it. Take ROMS. ROMS has a long legacy of including ice shelves. It was actually one of the first ocean models 12, 15 years ago to adopt an ice shelf. And we thought it's a straightforward exercise. We take ROMS melt rates, feed this into PISM, and PISM feeds back the ice sheet topography. And then this is adopted by the ROMS life and so on, so on. ROMS has a static ice shelf. We modified this to become a morphing ice shelf so that the surface will move, no problem. But then soon after that, we ran into something, we realized something that we could have realized beforehand. But and the realization is this cliff, if that's an ice shelf, that's this cliff. And the vertical coordinate system that ROMS applies, stretch coordinate system, doesn't like this, will cause errors. And I'm going to talk about this error and how to mitigate it in the duration of this talk. One of the advantages of using the stretch coordinate systems is that we can resolve the ice-ocean boundary layer under the ice shelf, which we thought would be an advantage to improve these estimates. And we also do a lot of work on the parameterization of the melting. That's actually where I come from scientifically. So this is sort of an expansion of my field of employment. So the stretching of these functions, I'm just going to show this quickly to show you this is sort of complicated, and why we choose the method that I'm going to present is related to the fact that this is sort of a big function. You could use a stretching that's just equidistant, like with a simple sigma function, equidistant layers, but usually in reality it looks like a stretching function of transformation. This S, which relies on sigma, another functionality of C that then has parameters of theta S and theta B that determine the pushing of resolution into the boundary, into the upper boundary or the lower boundary. And these models, these coordinate systems are prone to something that's called pressure gradient error. I think in this room everyone is aware of this. Local steep changes in topography are prone to numeric errors. The main reason, the reason of that is the reconstruction of the density profile, which if we have a strongly bent vertical coordinate system, that neighboring grid points rely on different support point densities to reconstruct the pressure gradient. Now we need to reconstruct the density profile. And of course the density is integrated to come up with a pressure gradient, and that should be ideally zero if we have a uniform stratification. And you can test this with models that have a strong bending of the coordinate system. You can test this with models. There should be no baroclinic pressure gradient in this, yet there still is a velocity that comes from this erroneous pressure gradient on the order of a few millimeters. Now this is a very simplistic test, but this error can get quickly out of hand, and it's not necessarily beaten by reducing the time step. Mentioning time step, one requirement for this type of coupling or for this this project was that we keep the ROMS time step, the ocean modeling time step, at a maximum, basically at the theoretical limit, to get fast outputs and don't occupy the supercomputers for too much time. So we're talking about realistic scales of 100 to 1,000 years, maybe. Right. So how do we measure this called hydrostatic stability? The literature gives us two numbers. One is Rx0, Rx1. They're called Haney and Beckman number. I never know which one is which. Doesn't matter. Rx0 is the simpler one. It's simply a relationship of depth, depth change over with relationship to the entire water column. And Rx1 is a more sophisticated one that actually looks at the Z layers, at the layers of our vertical coding system. These Rx factors are defined halfway between grid points, and if both nearing Rx1, for example, if both neighboring grid cells here share a level Rx1 is equal to 1, no problems. The literature gives Rx values should be lower than 6 or equal. You can run this to 10. It really depends on the application. Anyway, we need to limit this Rx1. Rx1 provides a good metric to assess the stability of a given modeling bathymetry and the chosen grid, and it's a local parameter. That's the important bit. So mostly when you look at the literature, when people run ROMS models, they talk about smoothing, selective smoothing, Shapiro filter, Laplacian filter. That works okay if you remove the ice shelf, because the only surface that is modulated is the bottom topography. But as soon as you add an ice shelf, you have two surfaces that can cause this error or can cause this bending of your vertical system. How are we? Time. Am I racing too fast? Or?
8 minutes into your talk.
So the second selective application of typical surface filters works for Rx0, but not for Rx1. And as I just mentioned, Rx1 is the one that we should focus on. And we need to treat the local problem of steepness between our neighboring numerical neighbors of our vertical coding system. So it needs a method that treats both the surfaces in conjunction and actually optimizes Rx1 rather than optimizing a surface or a boundary surface. So the method needs to be aware of the vertical stretching and its parameters. So let's simplify this problem to, as I said, it's a local problem between two neighboring cities. The approach is very simple. We change our ice draft. Rather than applying a filter, we change our local ice draft. And very simple, if Rx between these two cells exceeds an Rx max that we're given, that we're providing, we modify the ice draft, an I+1, to an I-I+1 to satisfy our Rx to become within Rx max. Now, there's either no solution or two solutions for this I-. No solution is, as I mentioned earlier, if our DH, if our bathymetry change at the bottom is too big, then no change of our ice draft will satisfy Rx. When it's two solutions, we can think of an I- that's higher than this cell or a lower one. There will be a point where Rx is exactly our Rx max on both ends. This is not symmetrical. An implicit assumption is that we have maximum or equal resolution in the boundary, in the bottom or in the surface. That's an implicit resolution, but that's the case for most of the models. Anything else doesn't really make sense for these kind of applications. So is there an analytical solution to find I-? There is, but you would have to derive these big transformation functionals for each and every different combination of these transformations, and that's a lot of work. And I wanted something where you can quickly plug in the vertical transformation function that you're using for your specific model and come up with a solution of this treatment. So instead of an analytical solution, we find our new ice draft from a 4D lookup table called capital Rx. Very creative. With a variable transformation, we define a water column, we define a DI and a DH, which we're no longer looking at actual bathymetry, the depth of I+1 or the ice draft at I+1. We're looking at a change starting from index I, a relative change. So Rx1 is now a function of the depth change, of the ice draft change, and the water column, and the ice draft in I, plus the stretch function. And now we do simple, it's a brute force mechanism. There's no elegance about this, sorry about it, but it works. So for a given stretching functional, we compute Rx1 over ranges of ice draft, water column, relative ice draft change, and relative bathymetry change. And for all this combination, we get an one. And that yields a lookup table for a given stretching. And now all we have to do, finding di by querying Rx for a specific Rx max. Not sure where we are. Sorry. So that's what it looks like. It's a bit hard to project a 4D table onto a 2D projector. So I've done half the work already. We're slicing this Rx lookup table at a water column of 233 meters and an ice draft of 700 meters, just some random values to demonstrate. And now we have left to find a DH that's already given. We know DH. We're not changing this for now. I will show you later how to expand this method to find DH as well. But for now, we assume DH is fine. Looking at DH, and then we find Rx max. Somewhere in here, we need to, along this line, find Rx max, and that gives us two solutions for DI. And then we need to come up with a strategy, which one of the DIs we're using. I usually use the one that has the same slope. So if it was before an upslope, I use the positive DI. If it was a downslope, I would use the negative DI. You can also see these solutions are not symmetric. That's kind of visible from the color. And we find a new I dash. So let's flick this to a top view. This is an idealistic ice shelf with a little bit of roughness sprinkled in. And these are the 2 points that I've just shown you in the vertical. Now, we do this method, this process. We apply this for the entire line along all the neighbors in either edge. And we start from ocean. This is open ocean surface. This is ice shelf. And the open ocean surface will not be changed because this will always be open ocean. We'll just basically carve our way down underneath the ice shelf. And we do this for one line. And the important bit to understand is we don't do this consecutively. We do this all concurrently. All the pairs of I and I plus 1 will be evaluated. And the update happens after we've done the entire line. And we do this for all the lines. And then, we rotate this. We do this in positive I direction, check Rx1. If our entire Rx1 is still exceeding Rx max, we come from this direction. So we propagate all the Rx1 violations throughout the surface, and it's a 2D problem. We check Rx again, and so we go in circles, not in circles, iterations, until Rx1 is satisfied over the entire domain. And for this specific example, this is a difference map. You see our Rx max is now 8.39. The target one was 8, but it's okay. We don't have to have a precise, we don't have to hit this number precisely. Within 10%, that's my personal preference, it's fine. So Rx max is now 8.29, and we've only modified 12% of the data points. So we have, we're sticking to, let's say, we're still close to the original data. We've only changed those points in the bathymetry that really violated. We're not applying some smoothing and in terms of unqualified smoothing. It's not an unqualified smoothing, it's a qualified smoothing. The whole thing, again, just in 2D, maybe to give a better demonstration, look at the left. That's the unprocessed data up top. In the middle, that's after an Rx1 treatment, the one I just described. And you see this is the Rx1 for each of these points. And only where the blue line is where the Rx max is, only where it was exceeding it will dampen it down. Everything else just stays the same. And these are the data points that were modified. So obviously near the ice shelf cliff, which was the initial problem, how we stumbled across this. Obviously near the cliff, we have huge changes of 60 meters to subduct our coordinate system underneath without violating Rx1. But then in between, there's only a few points that need to be changed. Now, there's a bit of a cheeky comparison, but of course I have to make this shiny. This is Shapiro, a second-order Shapiro filter that's applied to the entire ice shelf until the maximum Rx is, somewhere in the range of 8. And you see, we still have the maximum Rx at the ice shelf front, but everything else is smoothed out. There's no detail on this left. And with ice shelf models, detail is important because there's all sorts of melt effects that rely on the roughness, and there's just some studies coming out that the roughness is important. So we want to maintain the roughness. Results. This is a Ross ice shelf. That's where my research usually lays. And you see in this area, so this is treated with that RX1 method. You see in this area, Central and the Western ice shelf are relatively close to the data. I'm not saying to truth, because if data are truth, that's a different conversation. I'm not getting into this, but you see the suture zones are still here. The suture zones, we think, are conduits for ice shelf meltwater, for meltwater channels, and might be contributing to disintegration of ice shelves. So it's important to maintain these. And we even see some of these fracture zones here that are maintained because they weren't smoothed out. And obviously, big changes along the front and along the grounding line, because the steepness was too much to be modeled in ROMs. Now, how does this relate to coupling? Well, I started playing with OASIS. I thought I put the PISM and ROMs into OASIS, and that's 3 years back, and then I came across this problem, had to solve this first. So I ended up writing a bash coupler, because it seemed to be easier to bug fix this, and then ended up writing 7,000 lines of MATLAB code to do this RX1 rotating progressive forwards correction method. So the coupling step, is this the right? Might be not. Anyway, it doesn't matter. So as you can tell, regridding was the least of my problems. Unit conversion to ROMs conserves fresh water per individual ice shelf. The other way around, the coupling from PISM to ROMs at coupling stage, which is frequency every 5 years. Regridding, then we need to remove ocean narrows and tight corners where, a barotropic mode could get into some problems, and the RX treatment for each individual ice shelves. Conserved quantities are freshwater flux. I want to delete this, and not conserved is ice thickness, but we think we're getting away with it. And I think I wanted to demonstrate that it works. It's proof of concept, really. So it's a bit of a doomsday scenario. Under an 8.5 Nori-Zem forcing, the Ross ice shelf collapses in 2050. We all hope that's not going to happen, and there's obviously some other problems. But the message is, it works. We see the grounding line retreating. We see the ice shelf suddenly collapsing. So the communication between the two models works, and now we are back to the pathway where we make this a proper, more realistic model with by tuning the physics. All right. So summary and outlook: the RX1 correction method works reliably. It's relatively fast. At each coupling step, it takes about 10 minutes to run this correction method through all the ice shelves. It shows a minimum modification of the point that are delivered from PISM, and it shows a baroclinic ocean time stepping near the theoretical limit. And I cannot emphasize this enough, because that's important to model hundreds of years. And 20 minutes, I thought that was quite cool for 8 kilometer ocean model. Next step is to expand the method to correct both surfaces, and that's why I show you this again. So if you think these lines are the current DH and DI, and then you put a contour where Rx max is within this plane, you can easily come up with a shoot point within this square that's maybe close to the original ones, or is optimized by using minimum bathymetry change or something. All you need is a bathymetry to come from this point to a point within this, and you can use this method to correct both surfaces as you go in conjunction concurrently. And second step, implement in a suitable coupler framework. I guess that's what I'm here for. And my first question was, do I need to reprogram this whole thing in Fortran and make it a module to be able to run this in a live coupler? Or could I use some binaries and just feed a field to a binary and then use this within OASIS? That was our first choice, or something else. So yeah, I guess that's the conversations I'm going to have for the next 2 years, for the next 2 days. There's no thank you. That's the newest version that's not here. There should be a thank you for your attention. Thanks.
Time schemes at the ocean atmosphere interface.
So, I'm going to speak about the time stepping between ocean and atmosphere that we have in a model. Our community mostly use what I will call a parallel time stepping. That means that ocean and atmosphere run in parallel, mostly on a different set of processors or not. And that the end of a coupling time step, they exchange boundary condition, SST, sea ice cover, and fluxes. That means that when you run a coupling period, you use the boundary condition computed for the previous coupling period. That means, for instance, that the atmosphere will compute using the SST from the previous coupling period, and SST has seen the insulation from the previous coupling period. So you have a real inconsistency between the model and their boundary conditions. They are never synchronized. They always use boundary condition previously. This is never synchronized. So in your community, we mostly use two time schemes, the parallel time scheme I just described, and some of the groups use a sequential time scheme with atmosphere first. They first use the atmosphere and then run the ocean. This reduces the consistency, but that means that you cannot run the model in parallel, so you increase the time to solution, the sequential between ocean and atmosphere. So one brute force way to correct this is to iterate. At the end of the coupling period, you have new boundary condition, so you restart the model, you get the restart from the memory, you replay your coupling period with new boundary condition that are more up to date because they are for the correct coupling period. And if you think, you have to iterate until the convergence of the boundary condition. So it's real brute force because you have to run the model for one coupling period several times. It's a huge consumption of time. Why do we do that? So this Schwarz iterative method will give us a reference solution to evaluate the legacy time schemes that we have in our models. So it resynchronizes the model on the boundary condition. It's a mathematically consistent method, has a tremendous computing cost. Operationally, cannot do that. But we give a reference solution. And I will show the estimation that we can make of our legacy solution. So we have implemented such a method in the IPSL Earth system model. It was a real nightmare for the guy we have done that because you have to insert a loop in the model, writing the restart in memory. Nightmare. We have done that not in the operational model for Synopsys, but in a simplified version, low resolution to avoid too much computing step. And we have made 6 experiments parallel, time stepping, the sequential atmosphere first, and we have also tried the sequential ocean force to see what is. And we have tried with 2 coupling steps, 1 hour and 4 hours. This is very short run, and we run 50 iterations to be sure that you have a convergence. So it's cost of computing time for 5 days, but that's the problem. So what we will diagnose? This is the evolution for one point, for one coupling time step, the evolution of the sea surface temperature. So you start from the yellow dot, which is the sea surface temperature from the previous time steps. You do one iteration. One iteration is what the legacy time step will do. This is the solution we use in our operational runs. Then you iterate, and we can see a correction of the solution. In this case, the correction is bigger than the SCHISM, so it's a very huge correction. So we can compute the error that we do with the computing with the legacy time scheme we use in the model compared to a solution with this mathematically fully converged. So if we look, so I have made classes of error. On the left, you have smaller. The error is less than 1%. That means that the SSS change between two time steps, that's the term we diagnose. You have an error on the tendency, which is less than 1%. So what we see is 1 hour time steps is the atmosphere first is rather a good solution. In 80% of the cases, you have a rather low error. But for the parallel one, you see that in most of the cases, the error is 10%, and it can even be larger than the tendency term. You have some points where the error is very, very, very large. With 4 hour time step is even bigger. So we have very large error in the parallel time stepping. If you do 2 iterations, you see that you have almost solved the problem. In fact, that explains why the atmosphere first is working well. Because atmosphere first is in fact the same as doing 1 iteration on and a half. Because you have half of the problem of the synchronization of the solution with solved by atmosphere first. So it's mathematically the same as running 1 iteration on and a half. And as you see, in most of the cases, 2 iterations give a low error. So but it's an increase of 2 times of the cost of the models. So not a very good solution. So even with a bigger time step, you can have reduction of error is important. I have got the histogram of error depending on the local time. We have noon, we have sunrise, not 6 o'clock because it depends on the position on the Earth. Sunrise, sunset, and the error peak just after the sunrise. Then it reduces at noon and peak just before the sunset. So the error is really due to the fact that the ocean model sees the insolation too late. And then it sends back information about the SST. You have seen the insolation too late. So you have a negative error. The model does not succeed to hit the SST at the good time. It has a delay. Then, the contrary, at the end of the afternoon, it does not succeed to cool the SST on time. So you have a real strong signal on the diurnal cycle of the model, which you can see with this kind of time step. So, first conclusion. Time steps, the legacy time steps in our model are not mathematically consistent. So we have implemented a Schwarz iterative model in one version of the IPSS coupled model, mathematically consistent, and we use it to find a reference solution and to estimate the error made in our time scheme. The error can be quite large. With 2 iterations, you correct most of the error. So it will give us some idea of a solution, but first, I will show the impact on short experiment. These are ensemble experiments of 2 years run, but 50 members. And this is the difference of the SST simulated between the Schwarz direct simulation and the parallel method. And you can see error which can reach almost 2 degrees in some region. Or this is the mean between. If you plot, I have plotted some boxes where the errors are bigger. If you plot the time series of the surface temperature boxes, I have shown it for 4 experiments, one with a parallel time scheme, one with atmosphere first, and two simulations with only two iterations on 5 iterations of the Schwarz method. So you see here that with a few number of Schwarz iterations or with an atmosphere first time scheme, we have roughly the same solution. But the parallel one is really an outsider, and significantly an outsider. You can get a different climate with this time scheme, at least some different variability. And this is done now on longer runs. So we have not implemented Schwarz in the NRM model or in the IPSL standard model, but this is a difference in longer run between the sequential atmosphere first time scheme and the parallel one. I have this error is statistically significant. I won't show the p-value, etc. But it's clear that you have different. For the two models, it's not at the same places, but you can reach 1 degree of difference between the different solutions. So the effect on real experiment is also quite large. So what we plan to do now? So 2 iterations is probably a good solution. As it is an iterative scheme. For any iterative method, the solution can be improved, can reduce the number of iterations if you have a good first guess. Here, the first guess is the solution of the previous time steps. Can we replace the first iteration by some educated first guess of the sea surface temperature? That's something we are trying to do with some neural network. Only the second iteration. I don't have any solution to show, but for now, maybe I could advise you to use sequential atmosphere first time stepping if you can afford it. For instance, if you have some ensemble simulation where the time solution of one individual run is not important, maybe you can use that. For a model like IPSL model, for instance, it's a huge problem because the model runs on different set of processors. If you do an atmosphere first, that some of the CPUs will wait. If you put the 2 models on the same set of processors, you have a memory problem, for instance, and a load balancing problem because the number of processors for the 2 models. Maybe not that simple to do that. Okay.